The views expressed on Science for the People are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
Today, we are all about concrete. We'll talk to Dr. Cristina Zanotti about repairing and building better concrete structures. And later on, we'll discuss the Great Northern Concrete Toboggan Race with two of the organizers. But to get things started, we have historian Robert Courland about concrete's long history with humans and where we could learn from the Romans. Welcome to Science for the People. I'm Marian Kilgore. With me is Robert Courland, the author of a number of nonfiction books, but he's here with me today to discuss Concrete Planet, the strange and fascinating story of the world's most common man-made material. Thanks for joining me.
I'm happy to be with you, Marian.
So I'm sure at this point some of our listeners are picturing a gray, boring slab of concrete and trying to figure out how I plan to fill an entire show talking about it. So what's your background, and how did you get interested enough in concrete to write an entire book on the topic?
Well, actually, my background, my previous books, as well as Concrete Planet, are histories. And when I first mentioned to friends that I was going to write a book about the history of concrete, they thought I was kidding. And, yeah, sure, no, really, what are you writing about? And I said, no, it's a really fascinating story. And it affects all of us, because if you look at the world today, we build our buildings, sidewalks, dams, bridges, everything with concrete. And it was a technology that was perfected by the Romans, and then the technology, along with many others, were lost after the fall of the Roman Empire. And today it's very, very ubiquitous. In fact, it's the most common man-made material in existence. How it affects all of us is that there's two differences between Roman concrete and modern concrete. Roman concrete can last thousands of years. We have a number of Roman buildings that are still standing that are doing just fine. But modern steel-reinforced concrete, on the other hand, has less than 10% of the, perhaps 5% of the durability of Roman concrete. And the reason for that is that we put steel rebar in it, and eventually, through cracks or joints, moisture gets to the concrete, and the rebar expands. Imagine a root under a sidewalk, and as the tree grows, the root elevates the sidewalk and warps it. That's what happens when corrosion occurs on steel rebar. While it's being destroyed, it destroys the concrete around it. And so the lifespan of modern reinforced concrete is between 40 and a little over 100 years, perhaps 150 under ideal circumstances. Now, what this means is that we're constantly having to rebuild buildings, roads, sewer lines, and spending billions and billions of dollars, in fact, collectively trillions of dollars, rebuilding our infrastructure for each generation. It's nuts. The ancients could make structures that lasted centuries, but we can't even build roads that last a few decades. So we really need to address this problem, and no one's really interested in tackling it, unfortunately.
So you mentioned that the Romans had concrete, but I think a lot of people may not realize just how ubiquitous concrete is in our modern world. You mentioned sewer pipes, which I suspect a lot of people don't realize are made out of concrete in certain situations. So what would today's world look like without concrete? It would look
like 19th century. If you take look at a photograph of a city in the 19th century, that's what our cities today would look like without concrete. Now, concrete took off at the beginning of the early 20th century because it was promoted as being much more economical than brick construction. Back in those days, a solid building was a brick building, and it was more economical. You could do it quicker. And so in the matter of just a few years, no one was building brick buildings anymore. They were switching to reinforced concrete. Now, the advocates of reinforced concrete made claims about the material that just weren't true. One, that it's a forever building material, and they would point to the old Roman buildings and see, it can last centuries. Well, it doesn't. They also said that it was earthquake-proof. In actuality, more people are killed in concrete structures than any other kind of structures in an earthquake. A brick building may throw off a wall. A badly built brick building may throw off a wall in an earthquake, but the wall falls out, not in, and the people remain safe inside in most cases. Whereas a concrete structure a reinforced concrete structure will shake, it'll hold together, and then it reaches a point of catastrophic collapse, and most of the people inside the building will be injured or killed. So it's not earthquake-proof. Another claim they made was that it was fireproof. It's not. Concrete, unlike brick, which is born in fire, concrete, when exposed to high temperatures for even as short as half an hour or so, will fall apart. It's called exfoliation. It just can't hold up to high temperatures. So a lot of the claims made for it made it appear to the contractors and engineers at the time that this is perfect. It's the perfect building material. Well, it's not. And so we have to figure out ways to build our buildings and infrastructure using non-ferrous rebar. In other words, rebar that doesn't have iron, isn't iron-based. And we have alternatives, but people are not adopting them. And I think it'll take a government mandate before we finally start changing things.
Yeah, so, well, since we're here, let's talk about rebar and reinforcement a bit. So when structures are built out of concrete, they're not just a solid, uninterrupted slab of concrete, right? We put reinforcing bars in them. So when did that start happening, and what's the advantage of it?
The reason people thought that reinforced concrete was a forever building material was that, the steel rebar was surrounded. Rebar, by the way, is short for reinforcement bar. It was surrounded by concrete, so seemingly it was, protected from the elements. The other thing was that concrete cement, when it's drying, or I should say setting, and then it goes through a curing process, is highly alkaline, and alkalinity will prevent corrosion. That was something that was known back then. So it seemed like it was a forever building material. But unfortunately, through cracking and joints and so on, moisture can get to the rebar, and once corrosion starts, it'll quickly get out of hand. And the alkalinity of concrete cement disappears after the curing process. So after a few months, the corrosion-fighting qualities aren't there anymore. So that's why we're in this situation today.
Well, yeah, I mean, at work, when we buy steel pipe, sometimes we joke that we should just save the construction guys some time and buy the pre-rusted steel pipe. So I'd imagine the same sort of thing goes on with rebar, where it gets assembled in a building site and then gets to sit out in the rain for a bit and already start to corrode.
Yeah, in fact, I've lost count of the number of buildings I've seen that are built with rusty rebar. You watch them putting up the structure. They put in the rebar first and then pour the concrete. And the rebars are already rusted, so it's already got a head start. And so it's nuts. I mean, it's truly weird that the ancients could build better, more durable structures than we can today. But again, there's no movement to really change it. People are used to doing things one way, and they keep doing it the same way over and over again until there's either an outcry or a government mandate or something like that. And we need to really change that.
So maybe let's go back a ways. What do we know about when humans started using concrete historically?
It started, believe it or not, in the late Paleolithic. It was very crude concrete. Now, concrete is made of two basic substances, or I should say concrete cement is, and that is lime, which is also, we call it calcium oxide, which is probably the key element of concrete. And then a second element that's called the hydraulic element, which is mixed with lime, and that's usually clay or shale. And together they make something that's impervious to water. In fact, you can even build underwater with concrete because of that hydraulic element. But quicklime, calcium oxide, is really fascinating. It's you get it from burning calcium carbonate, usually in the form of limestone, at very, very high temperatures. And the result is curious. In fact, to Paleolithic people, it must have been magical, because here's a powder, and if you add water to the powder, it suddenly gets very hot. It generates a flameless heat. In fact, you can burn yourself with it. So that's so counterintuitive. You add water and it gets hot. And then after it cools, you've got a rock. You know, this, in their eyes, was really amazing. So what's curious about it is that you can only create lime with a high-temperature kiln. And so that means that Paleolithic people, just before the Neolithic period, say 12,000 years ago, before agriculture, when people were still hunter-gatherers, developed a high-temperature kiln long before they had bread ovens or woven cloth or metallurgy or even pottery. So it's how did they make the discovery? And I posit in my book that a shaman probably witnessed a lightning strike on a limestone outcrop and experimented with the powder that came as a result and discovered lime. And they would use the lime, mix it with rocks, just like we do with concrete today, and, make a floor with it, or something like that. Normally, it was used for flooring, and it worked. They discovered it 12,000 years ago. Now, it pops up here and there over the next few thousand years until ancient Rome. And the Romans, who are very practical people, when they discovered concrete, they said, hey, this is really amazing stuff. And they just went to town with it. And they built some of their most incredible structures using concrete. Probably the most striking one is the Pantheon in Rome, which is regularly listed as one of the 10 most significant buildings of all time. So the Romans perfected over a period of several centuries the use of concrete. So by the 1st century BC, they had pretty well mastered it. And they used it for practically every application. And unless it was deliberately demolished, the Roman structures still remain today. There's several of them in Rome itself. The Pantheon is the most striking, but the Roman Senate House was built using Roman concrete. And a massive harbor in Caesarea in Judea, which is today modern Israel, that was built using concrete exclusively. And it was the largest amount of concrete in a building project until the 20th century. In fact, the finished harbor looked very modern, just like the interior of the Pantheon looks very modern. You wouldn't expect that it came from the Greco-Roman world. And unfortunately, the harbor in Caesarea has sunk thanks to geological subsidence, and so it's now about 60 feet underwater.
So a project that large, so you were mentioning that they would have to have high temperature kilns involved for the lime. So what sort of size of project would that have been to build that harbor then? Because they would have just been burning, things like wood to heat up the lime to these high temperatures.
Yes, in fact, it was probably one of the greatest engineering achievements of the ancient world, because they had to have hundreds of lime kilns producing the concrete cement, and they had to ship from Italy the hydraulic element that the Romans used volcanic rock instead of clay or shale, and it worked fine. But they had to load up the equivalent of like today's super tankers with this pumice and ship it over to Judea. Then for the wood, for the fuel, and to make the forms that the concrete was poured into, they had to go up into the Black Sea and up the Danube and cut down a lot of thousands of trees and shipped them down by riverboat and by ship also to Judea. So it was a very complicated engineering process that resulted in something that it still amazes us today. In fact, we thought that the harbor at Caesarea was built of stone, and it was only when archaeologists put on their wetsuits and went down underwater and looked at the ruins that they realized it was actually made of concrete. And they could also, using DNA, look at the wood that was used, discovered that it actually came all the way from the Danube, and that the volcanic stone came all the way from Mount Vesuvius in Italy. It was a major, major engineering project.
So when we're talking about concrete, a lot of the time people are confused about what's the difference between concrete and cement and what goes into concrete. So what are the different bits and pieces of concrete that have to all get assembled for something, like the harbor to be built?
Well, there's the concrete cement, which is quicklime and kilned clay mixed together. And then there's what's called the aggregate. The aggregate is usually a combination of small rocks and sand. So the aggregate actually is probably between 75 and 80% of the finished product. So you hear people say, cement patio, cement sidewalk, and so on, when actually it's a concrete sidewalk and a concrete patio, because the cement only represents about 20% of the finished product. It'd be like calling a brick wall a mortar wall.
Well, and I guess that's another question. Mortar seems very similar to cement. Are they the same family of things? Is mortar just...
Oh, yeah. In fact, non-hydraulic concrete is essentially mortar, which is a combination of quicklime and sand and water. And then you throw in the rocks and so on. You can make monolithic concrete structures with non-hydraulic concrete. The only problem is that it'll gradually weather away, just like the mortar in a brick wall. Over a period of a few decades needs to be, what they call repointed, in other words, reapplied. And with the introduction of the hydraulic element, you've got something that will last indefinitely, assuming there's no steel in it.
So people might not necessarily think of concrete as a technology that has been developed over centuries. So what would make it, in your mind, a technology? What have people done over the centuries to improve it?
Well, what's interesting, which I also discovered in my research, is that the Romans knew things about concrete, how to use it, that we didn't wake up to until the second half of the 20th century. Among the things that the Romans did was they compacted the concrete after they laid it down. And this was to remove any air cavities and to make it as solid as possible. We didn't start doing that until the 1980s. The Romans also didn't use any ferrous reinforcement. Now, a lot of people think, well, that's because they didn't think about it. They didn't put two and two together and realize that rebar was, would make it much stronger. And I don't know that that's true, because the Romans and the Greeks did use reinforcement in their masonry structures, but they did something very interesting. They used these things called H-clamps that would fit between the blocks of masonry, embedded in one and then into the other, so they would hold them together. But they either made the H-clamps of bronze, which doesn't have corrosion issues, or if they used iron, they coated it with lead. And essentially, they galvanized it, which is something we do with rebar today. In some instances, we coat it with a layer of zinc, and this helps put off corrosion. Now, the Romans probably, and this is my opinion, it's not a universally held opinion, probably thought that iron and concrete don't go together and just avoided using it entirely. So they would fashion structures that didn't need iron reinforcement. So they always used concrete, for instance, in making arches or domes or vaults. in which the stresses were, drained off to the compressive components of the walls, or the load-bearing components of the walls. And this is why the Roman concrete structures have lasted so long, is that, one, they knew how to use it, and two, they avoided using any ferrous-based reinforcement.
So they made sure that all of their structures, basically, the concrete was always loaded so that it was getting pushed as opposed to pulled apart.
Yes, there's when you're doing a dome or an arch, you've got compressive forces that are transferred to the legs on each side of an arch, for instance, or to the walls if you're doing a dome. And you've got compressive forces because concrete is very, very heavy. And you've also got lateral forces because a arch and a dome tend to push out as well. And they overcame that with, using very thick walls, for instance, to dissipate some of that energy. And, for instance, in the Pantheon in Rome, they have surrounded the dome, the lower half of the dome, with several rings of bricks, which took care of the lateral forces as well. So they really knew what they were doing. And we have alternatives today. We have carbon fiber rebar. We have something called fiberglass reinforced polymer rebar. And we also have something called bronze aluminum rebar. Now, bronze aluminum is very interesting because it's an alloy that's as strong as the mild steel that's used in today's rebar, and yet doesn't have any corrosion issues. Now, it would mean that the building would cost a little bit more to build, but at least it would last much, much longer. So we can have our cake and eat it, too. We can use reinforcement, but we just have to eliminate the steel from it.
So in terms of maintaining modern concrete structures with rebar, I mean, shouldn't we just be able to patch cracks when they appear? Or is that's just buying extra time rather than fixing the root of the problem?
Well, it's worth buying extra time. We've improved the methods a bit. For instance, we can use ultrasound equipment to run over the concrete surface and look for corrosion that's just starting. And if you find it, you can hack away the concrete, brush off the corrosion with a wire brush, and then patch it with some fresh concrete. And that does the trick, but as you've probably seen with a few concrete structures, they're just full of patches, and it's a stopgap measure. They call it patch and pray, and that's very evocative, and that's essentially what we're doing. We're just putting off the inevitable, because there are places in a reinforced concrete structure where you can't easily reach.
Yeah. Well, and it's sort of funny to me because we have, I've seen things like steel bridges that, have been repurposed for a few different modes of transportation, and they're going on 100 years. Steel bridges are wonderful because the steel is exposed. It requires minimum maintenance. You just paint and repaint the steel. Occasionally you sandblast it off and put fresh paint on. That's why the Golden Gate Bridge is in wonderful shape, is that, we've been able to easily maintain it. The steel's there. You can see where there's any trouble spots. Whereas with reinforced concrete, it's often you don't know what's going on or where it's happening. So then,
By the way, I should say something. I've recently looked at some old reinforced concrete structures that are still with us today. They're a little over a century old. Thinking of the Ingalls building in Cincinnati, Ohio, the Church of Saint Jean de Montmartre in Paris, and some of Frank Lloyd Wright's walls. And I asked myself, why are they still around? Because they're over a century old, and that's really getting old for reinforced concrete. Well, what these buildings have in common is that they're clad in brick. So that's another possibility. You could take a reinforced concrete structure, cover its surface in brick or tile, and you've added an extra layer of protection, plus it probably looks a lot better, too. So that's something that we could do if we absolutely had to use steel. But again, it would cost a little bit more, but in exchange, you would have a building that would last much longer.
So then, with this discussion we've been having about sort of the weaknesses of using rebar to make concrete stronger.
Steel rebar.
Yes, steel rebar. Fair enough. The rebar that will rust and expand in volume thereby cracking your concrete. So I guess, can concrete be a sustainable building material?
Oh, yeah. Just get rid of the steel, or if you have to use steel, clad the building with an extra layer of protection in the form of tiles or bricks. For instance, the Sydney Opera House, you can imagine those beautiful, huge concrete shells. Well, on closer inspection, you'll see that they're completely covered in ceramic tiles. And, the Opera House is over 60 years old, and which is getting long in the tooth for reinforced concrete, but it seems to be holding up pretty well.
What about the kilning process with concrete? We're not burning a whole lot of wood to do it anymore, but we still have to get up to fairly high temperatures. So, these days, when we're talking more about carbon footprint.
Yeah, that's another dark side to concrete is that it's one of the largest generators of carbon dioxide. I mean, it's third place behind power plants and automobiles, but we're still talking about millions of tons of CO2 that's going up in the air every time we kiln the concrete. So that makes it doubly insane to have to build a concrete structure made with steel that has to be replaced every 50 to 100 years, because you're throwing more and more CO2 in the atmosphere by replacing, that infrastructure component or building. It's totally insane. That's another reason why we need to start building permanent concrete structures.
So in all of your research that you did for this book, what was the favorite concrete project that you ran across?
That's hard to say. I mean, if you ever go to Rome, you have to go to the Pantheon, because I've been all over the planet, and I've seen incredible, examples of architecture, ancient and modern. But the Pantheon, just every time I go there, it takes my breath away. In fact, when you go there, you'll hear other tourists nearby say, wow, or whoa, when you go inside, because you have this tremendous open space, and probably the most beautiful, at least on the interior, the most beautiful dome that's ever been created. And it's really, really amazing. But there are modern examples that I think are equally striking, and that's, if not for me, for other people, and that would be some of Frank Lloyd Wright's creations, such as the MoMA Museum in New York, and Falling Water in Pennsylvania, and also the Sydney Opera House, built by Jörg Utzon back in the 1950s. I mean, they're just brilliant architectural statements. And that I love concrete, don't get me wrong. I love concrete. It's just that we have to use it differently. We have to apply it differently. And if we do that, we'll save ourselves a lot of money, because right now we're building stuff that our children and grandchildren have to pay to replace. And also we're saving the environment. Well,
thank you very much for joining me. And I really appreciated the sort of narrative storytelling style of your book. It was a lot less intimidating than some of the technical concrete books out there.
Oh, no. I was determined to make it a good read for anyone.
So you can learn more about Robert Courland and his book on the history of concrete on our website at scienceforthepeople.ca. And we'll be right back with more Science for the People.
Science for the People is a weekly radio show and podcast that explores everyday life from a scientific perspective. We are a member of the Skepchick Network, a collection of blogs, podcasts, and video content focusing on science and critical thinking. To find out where Science for the People airs near you, or to listen to past episodes, check out our website at scienceforthepeople.ca. You'll also find links to support us at Patreon, to connect with us on Facebook and Twitter, and to subscribe to the podcast in iTunes. And now, back to the show.
Welcome back to Science for the People. I'm your host, Marianne Kilgore. Joining me is Dr. Cristina Zanotti, an assistant professor in the Civil Engineering Department at the University of British Columbia. Her research is focused on developing construction materials that are structurally effective, sustainable, and compatible with social and physical environments. And her current projects are focused on alternative cementitious materials, infrastructure repair, and construction for sustainable communities. So thanks so much for joining us today.
Thank you for having me, Marian.
So right off the bat, I think it's probably good to get people on the same page with why the repair of damaged concrete is such an important problem. So what's damaging our concrete in the first place?
Okay, that's a question which I could take an hour just to answer this part. So I believe you already made two very important questions. Why? The first one, why is it important to repair? And the second one, why does it deteriorate? So to answer the first part of your question, why it is important to repair, is that I believe that while we are so focused on reducing the carbon footprint of human activity, repairing a structure rather than building a new one from scratch is always a good solution in terms of saving materials. So saving raw materials, but also reducing the carbon footprint related to construction. So that's why many people would argue that striving to repair what exists is important. Not to mention when we talk about repairing infrastructure that is serving a community, you can imagine how difficult it will be to have to build a new infrastructure rather than being able to repair an existing infrastructure, which will be then unavailable for shorter amounts of time. So this is for the first part. The second part, why do concrete structures deteriorate? Well, there are several factors that affect reinforced concrete structure deterioration. So one of them, which I think is evident to everyone, is the corrosion of the steel rebar. So, and this corrosion is affected mostly by environmental attacks. So concrete per se is actually the perfect material, or the almost perfect material to put around a steel rebar, because concrete create a high alkaline environment for the steel rebars. So it has a quite high pH of more than 12. So the problem is that due to different types of chemical attacks, which I won't explain in detail, but probably many people already know, one of them is chloride attack, the other one is reactions with carbon dioxide. The passive barrier created by concrete around steel is basically undermined and reduced, and therefore rebar corrosion can be initiated. So that's one problem. Another problem is the deterioration of concrete itself. And even here I could mention 10 different reasons for which concrete deteriorates. One could be the loss of water to the environment, which creates drying shrinkage. Another one is the effect, for example, of the freezing water in concrete. As everyone knows, when water freezes, it expands, and if this water is filling the pore of concrete, this expansion will create deterioration of concrete. And there are also more chemical deteriorations. So all of these factors together are the ones that make our concrete structure look not so good after sometimes 10 years, sometimes 1 year, sometimes 50 years. So
what sort of buildings and structures are most harshly affected?
Well,
or does it vary wildly?
No, there are specific factors that can be considered. So first of all is the environment. So if you have a very hot weather, you will need to consider that the high temperature can create cracking of concrete at early age. If you are in a very cold environment, you really need to consider the effect of freezing and thawing. If you are by the seaside, you will have to consider the effect of sulfate attack from the seawater. So there is actually the concrete technology has been targeted to design concrete that is suitable to different environments. In general, we can imagine that a structure that is exposed will generate a larger vulnerability to rebar corrosion.
Right. So that's if you have like a wall on a building, then the closer the rebar is to the surface, the more likely it is to get damaged.
Exactly. And that's why it's very important to create a certain amount of concrete cover to protect the rebar from the corrosion. But there is another factor, which is the concrete design factor. So that's why there is so much work on concrete technology, because the concrete has to be good first. So when you don't use the right cement or you don't mix your concrete properly, for example, I mentioned how most of the concrete vulnerability is due to the ingress of contaminants. So if your concrete does, this type of vulnerability is summed up as transport properties of concrete to indicate the transport of different types of fluids. They can be liquid or gases or ions. So creating a good porosity and especially a good resistance of concrete to cracking so that this type of contaminants or water cannot pass through the concrete is extremely important.
Right, because once the concrete cracks, then if you get water in it and, we're in Canada, so it freezes, that just makes your cracks bigger.
Exactly.
So how can we go about creating structures or roads or, overpasses that last longer or are less likely to get damaged in the first place? We researchers and concrete technologies have been quite creative in the last 50 years. For example, a very effective way to prevent cracking is to add a micro reinforcement to concrete. So I don't know if you have ever heard about fiber reinforced concrete before. Fibers can be thought of as a smaller version of the steel rebar. So the steel rebars are put in concrete to make it more ductile and to prevent large failure due to the fact that concrete is a good material in compression, but has a very poor tensile strength and is very brittle. So fibers do the same. You take a material that is as brittle as concrete is, and we put some small fibers in it that basically are able to bridge the micro cracks and prevent them from widening or propagating. So that's one solution. So would those be like loose fibers that get thrown into the concrete mix when the water and the concrete are getting mixed? Oh, okay.
Exactly. And that's one way. There are many other ways. For example, to create a concrete that has a lower porosity by using proper supplementary cementing material, proper compaction. There has been also work on using different. There are studies on the use of rebars that are not made of steel. For example, fiber reinforced polymers that, of course, are not vulnerable to corrosion, but these are not applied as commonly as steel rebars.
So for the fiber reinforced concrete, is that something that you could do in addition to rebar? Or?
Yes.
Oh, okay.
So, more commonly in addition to rebars, but there are applications now where very good fiber reinforced concrete in terms of their mechanical behavior, of course, can be used without steel rebars. I don't know, let me know if maybe I become too technical, but typically concrete the problem of concrete is that when it cracks, the crack propagates. So it's a material that is unstable in tension. I usually explain concrete to my students, telling them to think of it as a cookie, both for the way it is done, but also for its brittleness. So you take a cookie, you break it and the cookie breaks, and you cannot put it back together. If you think about steel, you can bend the steel a lot. It's very ductile before it breaks. So that's why we need steel in concrete. Now, the fibers are small, so they're not able to provide the same amount of ductility that the steel provides. But recently, there has been a very intense work in optimizing the concrete matrix and the type of fibers used, such that although the concrete is not as ductile as when reinforced with steel, still it is able to resist failure after cracking. So this makes it a structurally reliable material, which in certain applications where the tension is not much, where you mainly develop, for example, a thin layer of, for example, for concrete pavements, or there are some structures in Europe that have been done, arch structures that therefore don't require, in which the concrete doesn't have strong tension, right, where actually the structure was very thin and free from rivers.
So because because they're shorter and smaller in diameter, you can't put as much force pulling them apart as you can with just a solid piece of rebar.
Exactly.
And then arches, I guess, yeah, that makes sense. They would be a good application for this because the loads are all in compression.
Yes, exactly.
Okay. So in terms of repair, how do you go about repairing a concrete structure that's been damaged? Or I imagine it depends on the type of damage, but say water has gotten in and started rusting the rebar. How does that get repaired?
Well, first of all, you need to take out the water, polish the deteriorated part, make sure that if that damage has taken place, it can be due to water. There may be a chloride contamination, so you definitely need to extract all the chlorides. And then you can apply the repair material, a new layer of repair, making sure that the repair material is actually compatible with the existing structure. That's the most fascinating and challenging part of designing a repair. When you add something to a system that already exists, this has to be compatible in a mechanical, physical, and chemical way to make sure that the old part and the new part together behave harmoniously and synergically, rather than the new repair actually accelerating the deterioration of the existing structure. So the challenges are the compatibility, as I mentioned, and the other challenge is the bond. So make sure that the repair material, once applied, doesn't debond quickly, delaminate quickly, which sometimes is problematic.
So you have to have a pretty good idea of what was done originally to build the concrete in the first place.
Exactly. And you also you need a pretty good idea of what damage your structure has, where the damage is, and how much damage you have, which sometimes is not easy to assess in a structure. Local location and quantification of damage can be challenging as well.
And if you have other repairs in the area, I'd imagine that complicates things too.
Yes.
So
that's why we enjoy doing it. Challenging.
In the news, occasionally we hear about historical buildings that are getting refurbished and repaired, and the price tags for those seem to be fairly high. So is it generally economical to repair buildings, or is it one of those things that it's easier to do early on but progressively more complicated the longer you leave it?
Well, it depends on the amount of damage, on the quality of the building. So if we talk about some historical heritage buildings, you cannot really quantify the value of the building. An historical heritage building is considered invaluable. So rehabilitating or repairing the building is considered culturally necessary. If we talk about the average house, well, sometimes it may not be worth it, but what we could do to avoid having to keep destroying and rebuild is to start thinking about durability, maintenance, and repair the day we make the new building. So make sure that there is a maintenance plan and that the materials adopted are durable, so that with time, the maintenance and the repair of the building is sustainable. The problem is that making a building that in the long run will be more easily and better maintained requires a larger investment in terms of quality of materials and design at the beginning of the construction. So sometimes such choice is not perceived as the most convenient, although in the long run it will be.
So what are some of the challenges in getting new materials or new repair or construction techniques into use by the construction industry?
I think the main challenge is reliability, right? So we need to be comfortable with what we use. And the comfortable thing about traditional Portland cement concrete is that they have been used. The cement used in traditional concrete is very well standardized. There is a myriad of results available on the behavior of this material. So we know what we are using and we are comfortable with the way it's going to behave. When you use something new, many properties are unknown. There is less comfort with the placement methodology. There is less confidence in something that is not known. So I think, the challenge is the lack of material available in terms of mechanical behavior or reliability of the material itself.
Yeah, so people are familiar with building and mixing concrete in a particular manner, and they need to get comfortable with a change to that methodology.
Yeah, especially, yes. Although I have to say that I'm seeing this is a very good time where, for example, I know you were interested in talking about low carbon footprint concrete. And this is such an exciting time from that point of view, both in not only academics, researchers, but also the industry is very much engaged and interested in developing new types of concrete, and I think there is a number of interesting research and also applications going on from this point of view. So I'm actually very optimistic because although it takes time, I can see how with time these technologies are being applied. Of course, initially they're applying at a smaller scale, but I can see how eventually this could become a larger scale application.
So what sort of new research are you most looking forward to seeing become commonplace?
Well, I believe alternative cementitious materials are an extremely interesting. If we talk about low carbon footprint concrete solutions, I'm thinking about alternative cementitious material. If we go back to durability and repair, I think there is a lot of exciting work right now on nanotechnology, self-healing, self-sensing concrete. This is also, I think, and this will be applied very soon as the technology, some is already being applied and more is coming. From low carbon footprint point of view, basically the most interesting and probably the most effective solutions are the one that where the cement in concrete is replaced with binders that have a lower carbon footprint. So rather than the Portland cement that we use normally, traditionally we now can use different type of binders such as geopolymer or magnesium concrete.
So you do some research into fiber reinforced concrete. Is that making its way out into construction projects, or will it soon?
Yes. Well, fibers are used very in several applications, either to improve the mechanical properties, either to prevent shrinkage. Okay. It's already quite common, but it could certainly become even more common. But yes, there are certainly many applications where some fibers are used to solve some of the issues that concrete may face.
So there's going to be let me rephrase that. So there's a lot of opportunity for changes and new technologies to make concrete construction better in the future.
Yes, I think as I told you, I'm probably optimistic, but I think that as we move forward, we're looking for more specific, for featured materials, featured solutions, and these require higher and better technology.
Yeah, fair.
My answer would be yes. I don't know if everyone agrees with me, but yeah.
Well, thank you so much for joining me. I appreciate it.
Thanks for having me.
You can learn more about Dr. Zanotti and her research on our website, scienceforthepeople.ca. And we'll be right back after this with two of the organizers for the Great Northern Concrete Toboggan Race.
Every week on Science for the People, we take the latest in scientific progress and relate it to people, our friends, our families, our communities, and our society. And we give researchers, authors, and journalists the time to talk in depth about what matters to them. If you love science but aren't satisfied with sound bites, join us again next week for Science for the People on your local radio station or anytime online at scienceforthepeople.ca.
Welcome back to Science for the People. I'm Marion Kilgore, and I'm here with two of the organizers of this year's Great Northern Concrete Toboggan Race. First is Andrew Tefs, a graduate student in engineering training at the University of Manitoba and vice president of logistics for the race. And we have Dave Barchyn, a professional engineer and vice president of communications. So let's start at the absolute basics for anyone who isn't used to snow. What is a toboggan, and what do they traditionally look like?
Toboggan is anything you ride and slide down a hill. It's usually long and flat with a little curve at the front. Anywhere from 1 to 5 people.
Yeah, basically a cross-section kind of like a candy cane, and then extruded maybe a foot and a half wide. Generally made out of wood, but obviously we are pushing the boundaries of that a little bit.
Right. So what's the point of the Great Northern Concrete Toboggan Race?
Well, I think it was kind of developed as an answer to the concrete canoe competition that happens down in the States, where they construct a canoe out of concrete. But since we have we're kind of lacking on our open water up in the north here, we had to resort to other means to come up with creative concrete mixes.
Mm-hmm.
So I imagine that concrete is a fairly challenging material to make a toboggan that slides down an icy hill on. So what sort of challenges does concrete run into when you're trying to do that with it?
Well, you have to pour it. It sort of comes in a liquid state, but it's pretty sticky and full of gravel, to put it simply. So shaping it can be a little difficult if you're trying to do a complicated curved shape. Other than that, it's extremely heavy, which can present some problems when you're trying to get up the hill.
Yeah, you got to come up with the right profile on your skis. As Tefs was saying, you got to have a nice contour to ensure that your toboggan will go straight. But you also need to distribute that weight properly so that you don't dig in too much and prevent yourself from moving at all.
So do the concrete toboggans these days look like the traditional candy cane shape, or have they changed over the years?
Well, the very first concrete toboggan races back in the 70s, they very much resembled your traditional toboggan, sort of a big slab of concrete that a couple of people would ride down on.
A couple of very brave people. No steering, no brakes.
Yeah, so in an effort to improve the safety rating of these sleds, we've made some pretty fundamental changes to what your average sled looks like.
Yeah, so these days, the only parts of it that need to be concrete are whatever touches the snow, excluding the brakes. So you just have to have little skis or a big slab of concrete on the bottom, and then you build an aluminum or steel or plastic. I think there was a carbon fiber last year, a frame over top, sort of to keep you from getting hurt if you fall over. And then you got a steering system, also usually aluminum or steel. So that's a big difference now, is no one gets hurt.
Yeah, think kind of a souped up GT with a roll cage made of concrete and steel.
Yeah, so that sounds like it's gotten a bit safer than just a straight up slab of concrete. Who rides these down the hills?
Students. So whoever designed it, and those will generally be the same people who built it. 5 at a time. They pile in, usually one driver and someone doing the brakes, and then the 3 others are just there for ballast. Get you down the hill a little faster.
Yeah, so we have participants from all over Canada and the States who participate in this thing. It's all engineering schools who have developed a program to put together kind of this project management type project to design and build and then race these sleds at a different city every year. So this year, of course, it's in Winnipeg, Manitoba.
So what do the students learn while they're putting these together? I imagine for some of them, it might be the first time they've actually made anything with concrete or with the aluminum and steel roll cages. Do they make all of it themselves? How much help do they get from outside, I guess?
I think it varies a fair bit team to team. Some teams will build everything themselves. They'll do their welding, pour their concrete. Some teams have a little more, slightly more complicated designs, and they might send it to a fab shop of some kind. But they do a lot of the construction themselves, which is, I think, the reason this competition is so great. Is it is a chance to sort of put your education to good use and actually see what goes into building something before you get out into the real world.
Is there a lot of... Do teams come up with their own special concrete mix, or are they pretty straightforward concrete pours usually?
Teams are always coming up with these great new concrete mixes. We had one year, there was a team, their theme was lifeguards, so they made a concrete that floats.
Oh.
As opposed to sinking quickly, which most concrete would do. So they used styrofoam balls instead of gravel, which made it very light instead of the typical concrete mix.
Well, yeah, the nice thing about this competition is that it allows teams to get creative with their mixes, right? Like you don't necessarily need to worry about building a road or something out of this stuff. If it fails, it's disappointing, but it's not the end of the world. So it allows the students to take some chances and kind of work outside of the traditional box that you would pull in your aggregates in your mix from.
And there's been a lot of really great stuff in the last few years on environmentally sustainable mixes. So using fly ash, silica fume, some teams have started using gray water as their water to mix with the cement.
So that would be, water that's being used, to wash dishes or something like that, where you wouldn't want to drink it, but it doesn't have too much going on with it.
Yeah, it's not hazardous, so to speak, but if it accumulates in a lake, it can be a problem.
So you guys have both been working with the race for a few years. So what did you learn making your first concrete toboggan?
Learned a lot about what really goes into pouring concrete. It's sort of thrown off as a given in classes sometimes in civil engineering. You'll get someone to pour this concrete and that'll be all good. So it's great to get your hands into it, to see your own designs fail, and then a month later see them not fail is it's a great thing for any student. So to get that experience of really designing something and putting it through the ringer.
Oh yeah, and it's a great opportunity as well to work as a team and need to rely on other people to hold up their end of your project, and because you end up kind of under the gun in the last few months to really experience what a stressful project can be like and have your team kind of pull through together. And even as Tefs was mentioning before, on a more kind of philosophical level, you do have some skin in the game, so to speak, right? Because you're going to be riding this thing down the hill. So
I think that counts as literal skin.
Yeah, literal skin in the game, right? So very very seldom do you see that as any kind of project manager. Often you do a project, you walk away, but this, if you've taken any risks or anything new, right? You have to sort of stand by your design quite literally and ride down the hill in this sled that you've put together.
Do you have a favorite story from the race over the years?
Well, there's an infamous case. You can probably find it on YouTube. I believe, was it
Alberta?
I want to say, a team that will remain unnamed for now decided to mount their braking system at the front of their sled, which I can't believe that no one kind of caught and said, guys, maybe this isn't the greatest idea. But
anyone who's ever taken a bike down a hill and tried to use only their front brakes, I'm sure you understand what we're talking about.
Yes,
flying over the handlebars.
So I guess the good news is when the brakes were deployed, they worked, but the bad news is that it launched the toboggan kind of back end over front end and completely flipped it over, resulting in a quite the crash.
Were the roll cages in effect at that time?
I believe they had a roll bar on the sled. Like no one was badly injured in that crash, but it's not unheard of to see a few broken bones due to failure of brake systems, but that's something we do try to avoid. With the roll cages, we have some teams have seat belts in there as well, and of course everyone in the sled has a racing helmet on. So it's about as safe as you can make riding a 350-pound concrete sled down a hill.
That's a fair statement. So thanks very much for joining me, both of you.
Thank you.
You're very welcome. It was a pleasure.
So if you'd like to learn more about Dave, Andrew, and the Great Northern Concrete Toboggan Race, you can follow the links from scienceforthepeople.ca. Thanks for listening, and we'll see you next week on Science for the People.
Science for the People is produced by Rochelle Saunders and edited by Ryan Bromsgrove. Helen Quivalon is our publishing liaison. We get research help from Josh Witten and consulting support from Desiree Schell. Our frequently seen guest hosts are Marion Kilgour, Anika Hazra, and Jessica Yaros. Our theme song is called Binary Consequence, and it was written and recorded by Fractal Pattern. Science for the People is entirely listener-supported. You can find us on Patreon, where you can support us with monthly donations in any amount, or you can send us a one-time donation in any amount via the donate page of our website. Science for the People is created in partnership with the Skepchick Network, a collection of blogs, podcasts, and video content focusing on the intersection of science, popular culture, politics, and social justice. You can find out more about Skepchick at skepchick.org. The show is hosted by science news writer Bethany Brookshire and me, Rochelle Saunders.